Perfect timing. All right. How's first week going for everybody?
Surprisingly busy.
Busy, keeping things going?
Yeah.
Hanging in there?
I need to stay busy. I don't feel insane. That's my workload. It's all online, so it's watching a lot of video. Discussion posts. Yeah, Larry videos. He really made it wrong.
Appreciate that. You're welcome to hang out afterwards if you want to talk. We'll start with just a little bit of we're gonna be dealing a lot with alkenes now. Because that's gonna be our starting material for all these different addition reactions. So figured we'd remind ourselves how the nomenclature worked with these. Just a reminder, we'll use the term cis and trans, but when we're looking for the systematic name, we're typically looking for that E versus Z nomenclature. Which means we're using the priority system that's similar to RNS, where you're looking for that, you're assigning priority based on atomic number. And the difference between cis and trans is always talking about the longest continuous carbon chain, not necessarily anything to do with other atoms like oxygens and things like that. So, but E and Z is the more universal. That's kind of the new school way of doing it instead of using cis and trans for the alkenes. So we'll try and stick to that. But that's a system that's new since I learned this first time. So I'm still probably going to slip up and call it by the old school name because that's how I learned it.
So what's E?
Sorry, reminder. Yeah. E
So I haven't
was
used this nomenclature.
entgegen. Didn't we define this at some point last quarter? I think a little bit. Entgegen means against in German.
Oh.
It's the same thing as saying, it's the same idea as trans, across. Versus Z is Zusam. There might be two M's there. My spelling in German is pretty shaky.
I probably forgot. I would imagine we went over it, but
so Zusammen is like cis meaning the same. But the difference, the reason why we switch it over is because these two, E and Z, are referring specifically to that priority system on atomic numbers. Right, but it's the same general logic as cis and trans.
I remember seeing that you said on the same side.
It's the same side, yeah, in the bad French accent. And that'll be the last time you get me to do that. The one that still crops up in my head from when I was 15 years old and I took chemistry for the very first time, the lab safety video was talking about litmus paper and the color of litmus paper. How do you know it's if it's blue litmus paper and it turns red, that means that your solution is acidic. And if it's red litmus paper and it turns blue, it means it's basic. And the way this really, really cheesy video got me to remember that for the last 20 plus years is in a bad Southern accent. You say, blue to red, acid.
That's amazing.
And I've never been able to forget that ever since. I still, when I need to remember it, I still come back to that one. All right, let's name these things. No, they had more markers in here. I might have to go run over to the instruction office and get some more if these ones aren't any good. So just like always, longest continuous carbon chain, right? Which with the alkenes, the alkene group actually gives you, and to be more specific, when we start adding more functional groups, we're going to want the longest continuous carbon chain that has that functional group in it. If there's a possibility of having a longer continuous carbon chain without the alkene, that's not continuous. We want the longest continuous carbon chain with the alkene. So in this case, so that actually gives us a way that we can kind of orient ourselves because we have two options here, right? And it's really easy to see which one of these is the longer direction. So it's going to be right there, and then on the other side, we have 2 carbons or 1 carbon, so. Go the 2 carbon route. Brown's not much better than the green. Your instructor life struggles is somebody else is using this classroom. And they used up the good markers, they took them with them when they left. First week of class and already things you get cut through. Cool. So 1, 2, 3, 4, 5, 6, 7. So it's gonna be heptene. That one's okay. Or hept, whatever ene, because we also need to specify where the double bond is. And we want to keep the double bond number as low as possible. So it's not just about keeping, now that we have a one sort of dominant functional group, that's the one that we're gonna try and stick to. Keeping that number as low as possible. So 1, 2, 3 versus 1, 2, 3, 4. So we're gonna call it 3 heptene or hept3ene. And that means we're counting from this direction. There's our carbon 1. We're gonna stick to that those numbers for the rest of the prefixes. And this one is actually, they're all methyl groups, right? So it's gonna be tetramethyl. And it's on carbons 3, 4, 5, 5. And just like we've done in the past, if it's tetramethyl, we need 4 numbers. We gotta specify where all of them are. All right, then the last piece here is just, is it E or Z? So our priority here, in this case, there's nothing there but carbons, so it's the same as saying cis-trans. No long as continuous carbon chain is also going to be our highest priority. So this is going to be trans or E. All seeming familiar, relatively comfortable. The time we don't really need to worry about E and Z is with ring structures, because we're pretty much always going to assume that these ring structures are in this Z configuration. It is possible when you get to 9 carbons or more in the same ring, you can actually have an E stereoisomer in a ring structure. But they're pretty rare and unstable. So we don't usually specify for cyclohexene. So we're naming this one, obviously the longest continuous carbon chain that has the alkene is going to be cyclohexene. So it's going to be 1 ethyl. So both of those, you do have to be careful with these, with numbering. But because either one of these carbons could be considered carbon 1 and they're identical to each other until we attach the ethyl group, we don't have to say anything about that.
Would you kind of just assign
Right,
whatever starting point
right.
that you?
If we did that, that's where you
Then
really
that's
have to
where-
be careful, because 1 and 2 have to be on either side of the double bond. So you can't say this is 1, 2. Because if this is 1, that's 2, or the other way around. So if we were naming this one, we'd probably say 2 ethyl, 3 methyl. Start counting here, keeps those 2 numbers lower. But again, the main thing is we want to keep the numbers as low as possible. The main thing is that we're being unambiguous, so that if somebody read what we wrote, they'd be able to get to the right structure every time. Even if there was a different way to count, as long as your way of counting gets you to the right number, it's, especially for these ring structures, that's the biggest deal, is that you can get from the name to the structure.
So we wouldn't have to worry with that, like 2, 3, or 1, 6, so I would be.
2, 3 would make more sense, we would usually say.
The sum's lower.
Yeah, because this, the sum is lower of those. If you said 1, 6 cyclohexene, people would still be able to get to the right structure though. So that don't focus too hard on the numbering, that you lose sight of what's most important. Here's a case where the cis trans is different than the EZ. Right, because the longest continuous carbon chain goes that way, the longest, so this would be cis. But it would be E, because the chlorine has higher priority than the methyl group on this side. Alright, so 1, 2, 3, 4, 5, 6, 7.
And that's because of atomic weight, right?
Because that's atomic number
Or
technically,
atomic number, yeah.
number of protons, not just the weight. But so even though we would, we still count this as far as counting our longest continuous carbon chain, as far as saying whether it's and the longest continuous carbon chain is cis. But if we're assigning priority between the methyl or the chlorine has a higher atomic number than the carbon does. So the chlorine has the higher priority. It's kind of a weird, it's a little bit of a shift from just thinking about longest continuous carbon chain, but this seems to be the way that all of the nomenclature is heading. This is the common way of doing it now, so we're gonna try and stick to it, like I said. So this one would be E. To chloroheptene, to heptene. And I think this is one of the reasons why they wanted to get away from the cis versus trans is actually because that leaves you free to talk about cis trans as being on the other side of the ring. E and Z specifically is talking about alkenes. So if you have a molecule like this, where you've got a ring structure that's got to have a cis trans and you've got an alkene as well, it allows you to distinguish verbally. Are we talking about the substituents on the ring or are we talking about the alkene part? Because they haven't phased out the use of cis and trans when it comes to talking about ring structures, only when they're talking about alkenes. Or maybe they just haven't gotten to that yet.
That will last. There, I guess in Carlos in it, and then.
Yeah, this is gonna have an R and an S, not a cis first, not an E or a Z in this case, because you have one stereo center.
And then I forget, is for determining the priority, sp2 carbons have a higher priority than sp.
Yeah, there's some convoluted way that they say, like if it's got a pi bond, you can go backwards across it or something. Like there's some weird way that they describe it, but basically this is a more important functional group. I like thinking about it as sp2 carbon. It makes more sense. An sp2 carbon is going to be a higher priority than an sp3 carbon. Did you see that in one of the online resources or something to describe it like that? Because that's actually more succinctly put than any of the other textbooks I've read it in.
You know, I remember it being weird, the whole like go back on the bond thing, but I was just thinking about it in terms of like what kind of carbon. Because I guess if it was like if the one on the left, the sp3 carbon had like 2 methyl groups on it, that could be different, right? Because then the sp2 carbon would have 1 hydrogen, whereas the sp3 carbon would be bonded to 3 carbons. So then it's like, right. So I like the sp2 having the higher priority. I think that makes more sense. Basically, the way I've always thought about it is the more important functional group gets the higher priority. And when we're talking about these, that's more reactive. That's a more important functional group than just alkanes. So I would put the higher priority here. And I like your sp2 as a good way of thinking about that. So just a reminder how we do R versus S. So this is going to be
3-bromo cyclohexene. And then it's just a question of is it R or S? So our priority here, 1, 4 is the hydrogen that's already into the back. Then we have 2 and 3. So it's gonna be R. So R 3-bromo cyclohexene. And this is another one of those ones where you have to be careful with your numbering. It seems like you could call that carbon 2. Because, well, that's carbon 1. But 1 to 2 has to be across the pi bond. So if that's 1, that's 2, that's 3, keeps the number lower. Then if you call that carbon 1, this has to be 2, which would make it 6-bromo. All right. Feeling good on nomenclature? It's kind of it's one of those skills that as we keep adding trickier and trickier mechanisms and concepts, it'll feel like your safety blanket to go back to nomenclature, because it's just nomenclature. It's tricky sometimes, but it's not, it's complicated, but it's not that tricky once you know the rules. All right, so the first, let me clear the board here. The first mechanism we're going to add for alkenes is what's called electrophilic addition. So we've dealt with nucleophilic substitution and nucleophilic elimination. We haven't done anything that's really electrophilic yet. But it's the same general idea. And the only reason why we have to use the term electrophilic is it is kind of still a nucleophilic attack, except that in this case, our organic molecule is going to act as the nucleophile. And so since this is OChem, we usually talk about things from the perspective of, or from the frame of reference of the carbon-based molecule. The carbon-based molecule is going to get attacked by an electrophile. Which makes sense, it's got a whole bunch of electrons in this pi bond just sitting there, right? We know pi bonds aren't quite as stable as sigma bonds, there's not as much orbital overlap. So if we've got a pi bond sitting there, it makes sense that if there's a strong positive charge floating around, it's going to be attracted to those electrons. Another way of thinking about it is that our alkene can act as a base. It can accept a proton. Or in Lewis base terms, it can act as an electron donor. And so the primary mechanism here is basically these electrons are actually going to be moving towards a positive charge. But then you have to make room for it, just like with an SN2, we had to draw 2 arrows and when we had a nucleophile attack, right? To make room for it in the valence shell. So we get your good draw, there it is. Your pi bond electrons move towards the hydrogen, and then the bromine takes the electrons and leaves. So the bromine acts as a leaving group. So this is, you could consider this a proton transfer step. It also looks a little bit like a nucleophilic attack by the pi bond. This is just the example that I used for starters. Yeah. So once we get that, if we carry out the results of this pi bond moving over here, the pi bond moves to make a new carbon hydrogen bonds. That broke a carbon-carbon pi bond to do that, right? So we added this new carbon hydrogen bond right here at the expense of breaking up a carbon's full octet. Because we only have a finite number of electrons we're working with, right? And then, so that effectively leaves us a carbocation, and now it actually looks like the last piece of an SN1, right? Once you have a carbocation, if you have a negative charge around, it's just gonna come in here and bring its electrons and attach. Draw through the arrow on the wrong side. Right, so not that complicated of a mechanism. It's kind of similar to an elimination happening backwards, right? In the elimination, we would have the opposite of this step happening first. We'd have the bromine leaving first to give us this molecule. And then we would have these electrons moving toward the carbocation to make the pi bond. Right, so it literally is just an E1 in reverse. So which of these would we expect to be the slower step, the rate determining step? Where's our bottleneck here?
Probably the first one, because
Yeah.
that's pretty simple.
Well, and this is pretty unstable, right? We're making something that's less stable. And then once we make this intermediate, it very quickly is going to react with something, right? To fill that carbon's valence again. So yeah, the first step, just like with E1, the first step was making the intermediate because it was less stable, right? Here, we've got to make the intermediate, which is less stable, and then it can go downhill in energy again. So if we think about the potential energy surface for this reaction, we have our energy scale here. Reactants are going to go uphill in energy to make an unstable intermediate, and then make products. The slowest step is going to be that first one, making the intermediate. And if we're going backwards, the same is true, right? And that's what we're just talking about. Making the intermediate for the elimination was the slow step, and then it's downhill in energy, either direction. All right, so questions so far? It's all seeming like it makes some amount of sense. So this is just looking at, if we're thinking about these reactions as just the addition is the opposite of the elimination, it is an equilibrium process. You can have this reaction happen in both directions relatively easily. Because we have, this is our potential energy surface, right? If it can happen forward, it can happen backward. Right, so starting from an alkene and a hydrohalide acid, the addition gives us the halide product. Elimination removes the halide and gives us the back pi bonds. So which of these, if both of these are an equilibrium reaction, how can we shift the equilibrium one way versus the other? Can we? Or are we just kind of stuck at equilibrium?
If you shift pH, there would be more. I don't know.
So the Chadwick is principle, right?
I think that's gonna affect how much more addition is created.
Yeah,
So
so
if you make it more basic, there would be more elimination.
very good. More basic is going to favor more elimination. And so we have the Chatelier's principle. We also have the fact that we can change the temperature too. That's the entropy term. Right, so last quarter we decided that high temperature favored elimination for entropy reasons, right? Which kind of makes sense when we look at this these two options, it's a little bit harder to see with the substitution versus elimination distinction, because it kind of looks like there were a similar number of pieces on both sides, but for this, it's an equilibrium reaction, it's really easy to see. Two independent molecules versus one molecule. This is gonna have higher entropy. This is going to be favored by entropy. The reactant side, as it's drawn here. And as you get a larger temperature, your entropy term matters more. So even in addition, so Le Chatelier's principle, like we discussed, that's all, if we're keeping it the same temperature, we can still favor products versus the reactants by changing pH. But we also have the additional tool of, if we change temperature, we can even more strongly favor one side versus the other. At a low temperature, the entropy term becomes less important. And what's going to be favored by enthalpy between these two sides? Why, David?
Because just the amount of energy that's going to be stored in the bonds, I think it's going to be more energy stored on the right side. What addition?
So favoring this product.
Yeah.
Yeah, and so one of the easiest way to keep in mind or to predict ahead of time which side is going to be favored by enthalpy is if there's a difference in the number of sigma bonds. A pi bond is not as stable as sigma bonds, because sigma bonds allow you to get those orbital overlaps a lot more cleanly, right? And so having everything as sigma bonds, we get extra sigma bonds. This is going to be more stable based on enthalpy. Nobody actually says enthalpy. I'm just trying to overemphasize. So, a pi bond is going to be less stable based on enthalpy, but it's going to be favored by entropy. Right, so this gives us a really convenient way to kind of lean on the reaction to favor addition versus elimination. High temperatures are going to favor the elimination, low temperatures are going to favor the addition. And the other way we can do this to kind of, in addition to using pH, the other way we can kind of control this is if we have some way to remove this product. If we can change as this is produced, if we started here and it goes through an elimination, if we had some other reaction present or we had some sort of reaction conditions that allowed us to remove this as it was being made, that's another way. So it's not, remember, Le Chatelier's principle is not always just about adding more reactants or adding more products. Sometimes removing a reactant is actually more powerful, because that can be an ongoing process, right? So in this case, not only would the higher temperature favor this side of the reaction, most of these hydrohalide acids are actually pretty volatile. They'll evaporate off pretty easily. So especially if this was, say, HCl is a gas at room temperature. So if you can just heat it to get that HCl to evaporate off and be in the gas phase or be sucked out with the vacuum pump, you can actually be removing this and keep driving it to the left as well. So we have several options. The main one I wanted to talk about for this lecture, though, was these two. So I wanted to make a point: more sigma bonds is favored by enthalpy. More molecules is favored by entropy.
You also precipitate out the halide with like silver.
Yeah. That's another good way to do it. If you removed you could remove your halide by adding, you have to be careful in organic chemistry because a lot of the same metals that we would use to precipitate out a halide are also catalysts in organic chemistry. We're going to talk about mercury later on in this lecture, but mercury itself catalyzes a different type of addition reaction. So metals, you've got to be careful with that. And even with this one, even adding heat to get it to evaporate, we want to be careful with it as well. Because this is going to be relatively volatile too. We don't want to boil off our product along with what the hydrogen halide we're trying to get rid of as well. All right, so this is just going through that same logic. And we can actually estimate the overall delta H of the reaction, because pretty much all, like every carbon chlorine sigma bond is going to be slightly different, but they're all going to be in the same ballpark. An sp3 carbon forming a bond with chloride is always going to have about 84 kilocalories per mole. This is in kilocalories, not kilojoules. Organic chemists tend to work in kcals instead of joules. I'm not sure why. But the main point though is that even though the rest of the molecule may change, we can just look at, okay, a carbon-carbon pi bond is about 63 kcals per mole. A carbon-hydrogen bond is about 101 kcals per mole. A hydrogen chloride bond is about 103 kcals per mole. We just sum these up. The ones in red are the bonds we're breaking. So we have to put that energy in. That makes that a positive number. The bonds we're forming, we're going to get that energy out. So those are a negative number. When we sum all that up, bonds broken are positive, minus bonds formed, because those are negative. We get an overall negative 19 kcals per mole. Which, and again, just to put it in kilojoules, because we also deal with kilojoules a lot, kcals are about 4 times smaller than kilojoules. Roughly, it's that 4.184 number, right? Is our conversion. So it's going to be close to negative 80 kilojoules per mole. Which is not strongly exothermic,
But it's exothermic.
but it's exothermic. Yeah. If you wanted an idea of what that's going to do to the equilibrium, what the equilibrium constant is going to be, we can use that K equals E the minus delta H over, it's technically delta G, but usually the entropy term is relatively small. But if we just plugged in negative 80,000 for delta G, and then R is our 8.314, and temperature, call it room temperature, so call it 298. We're going to get a fairly large K value for this. We're not talking anything crazy like 10 to the 30th or something like that, but definitely favors products fairly strongly. When I was in grad school doing computational chemistry, all of our numbers, we always got raw energies out when we were doing, a big chunk of what we did was calculating these values based on the optimized geometries. But then to put it in terms that the experimentalists like to think about, we would then have to throw it in here. Because this winds up being the way that we can actually measure things. Or work backwards from a measured number to get to an energy. So basically, this is one of those key equations that connects the experimental with the theoretical. And then I didn't put any numbers to it. But as far as the entropy term, you just count the number of molecules on both sides. 2 to 1. This has a lot more entropy than that does. If it's the same number of molecules, sometimes we need to consider what phase they're in. Gases have more entropy than aqueous, which has more entropy than liquid, which has more entropy than solid. A mixture is always has more entropy than any pure substance of the same phase. Basically, because if it's a mixture, there's more ways you can arrange things, right? But in general, for OChem, we're mainly going to look at things we're gonna talk about them mostly in the gas phase when we're talking about these energies. Or at least they're the same phase on each side, so it doesn't really matter if they're dissolved in a solvent or if they're a gas, it's the same general idea. All right. Who's ready to see your first complicated mechanism? We'll go through it once, then we'll take a break and we'll come back and we'll do it again. And then we'll do some practice with it. All right, so the net reaction here is called oxymercuration, demercuration. So it's two steps, your oxymercuration part, and then you got to get rid of the mercury. We don't want to leave the mercury attached. All right, so the oxymercuration part, it's going to start as an electrophilic attack, just like we did before, except instead of just a hydrogen attaching to break up pi bonds, that we use this catalyst, mercury 2 acetate. This mercury 2 acetate, the mercury winds up being a large enough molecule. It's positively charged and has room in its valence shell to accept electrons. And it's large enough that instead of just breaking both or breaking the pi bond and making a single sigma bond, it kind of makes this three-sided ring. We don't see that with the hydrogen because the hydrogen is just physically too small to be in that space. But mercury being large enough of a molecule, being a heavy metal and having those d orbitals, allows us to make this three-sided ring. So it's not as unstable as making that full carbocation. All right, and that winds up being a common sort of reaction motif that we'll see in some of these. The larger molecules wind up being able to make these three-sided rings temporarily that are slightly more stable. So if I was drawing the arrows here, we basically just wind up with the pi electrons moving towards the mercury, and we just kick off an acetate at the same time. Acetate is relatively stable on its own and makes a really good leaving group. So then we have this mercury three-sided ring. We still have one of the acetates attached just because the mercury's got a positive charge. It's drawn as a negative charge here because the mercury has 3 bonds to it. We're not really worried about the charge on the mercury as much though. But then what happens is if we've got a carbon mercury bond, the mercury actually winds up pulling electron density towards itself. The reason that mercury gets used in this and not something less toxic is basically because the mercury kind of hits that sweet spot of being electronegative enough of a metal that it can make a fairly strong covalent bond with carbon. Most metals won't do that, right? Most metals, if you put them with the nonmetal, the difference in electronegativity is such that you wind up making an ionic bond instead, right? But some of those metals that are close to the stair step on the periodic table wind up being able to make these covalent bonds with carbon. And that actually creates a partial positive on both of these carbons because your electron density is all pulled to one side of the molecule. And that means that this creates a good place for an oxygen to come in and attack, right? Because the oxygen's got a partial negative on those lone pairs. So your oxygen's basically just going to come in here and attach to one of these 2 carbons. That allows the mercury to keep those electrons and break that pi bond. So we wind up with an OH attached to one of our carbons that was part of the pi bonds. And then we still have the mercury attached to the other one. All right, so again, I managed to place the figure right on the edge of the board here. But the net result of this first one is you break the pi bond and you add the mercury acetate to one side of the pi bonds and you add an OH to the other side of the pi bond. And then the second step is just to get rid of the mercury. The demercuration part just removes the mercury and we're left with the alcohol. Right, so this is the net result of this reaction is what's called a hydration. You hydrate if you hydrate yourself, you add water, right? Hydration reaction is the same thing. We broke a pi bond and we added a water. We added it as an OH on one side and a hydrogen on the other. But the net result is water plus an alkene gives an alcohol. Alright, so this is just a specific version. There's actually several versions of hydration reactions that we're going to go over. This version is called oxymercuration, demercuration. The demercuration, you basically just come in here with what's called a hydride, sodium borohydride. It's a hydride because you have hydrogen attached to something less electronegative than it is. When you have a hydrogen making a covalent bond with something less electronegative, with a metal or a boron, you wind up with hydrides, which is just a hydrogen with a negative charge that can then act as a nucleophile. And so you wind up with, in this step, what happens to the mercury and the rest of it in this step is a separate reduction reaction. We actually wind up producing metallic mercury. We just reduce everything in there. And your hydride winds up coming and doing an SN2 basically. And it basically just pushes the mercury off to add a hydrogen to the carbon where the mercury was attached.
So from it being a hydration reaction, it's usually you add water with the alkene first, right? Or is
Calling it a hydration is referring to the net result of the entire thing.
oh okay.
Right, so we added, and I didn't show this step, our intermediate here would actually be in oxygen with 3 bonds and a positive charge here, and then we would have a proton transfer to kick off a hydrogen, right? So in this step, we actually add an OH. And then in this last step, we add the hydrogen to give it a net result of an adding an H2O.
Okay.
But we do it in multiple steps because that's what's more stable.
With the mercury intermediate on the product of the first step, is there a reason why, why the oxygen is attacking that middle carbon rather than the terminal carbon?
Yes. So, and that is, remember Zaitsev's rival, Markovnikov?
Yeah.
This is Markovnikov's rule.
Okay.
When you have, if you're going to add an oxygen in an addition reaction, if you're going to add anything in an addition reaction, you tend to add the non-hydrogen piece, the more substituted carbon. And basically, it's because the same reason that a secondary carbocation is more stable than a primary. We have to go through a transition state. If we're going to add it to one of these 2 carbons, one of those transition states is going to look kind of like a carbocation. So if we've got to have an oxygen come in here and attach to one of them, it's going to be the more substituted one, just because that's the one that's going to be more stable as a carbocation. It doesn't form a full carbocation, but it kind of, the transition state energy kind of looks like that. So if we have to choose between these 2 in a Markovnikov reaction, which most addition reactions are, we'll go through the anti-Markovnikov later. You're almost always going to add your non-hydrogen piece on the more substituted carbon. And that applies to that first one we looked at too.
So it's kind of like because the more substituted carbon, because it has more carbons around it that are electron withdrawing in a sense, like if they're able to it's able to have more of a delta plus
It's actually that it has less of a delta plus, but that actually makes this bond weaker. This bond is weaker because it has electron donating
Oh, okay. Okay.
stuff around,
Oh, gotcha. Right.
which makes it, it's a little counterintuitive because that makes it less attractive for the oxygen to come in and attack,
Yeah,
but it also makes it easier to break.
so it's the lower activation energy.
Yeah.
Is what matters there more than.
Exactly. So that's exactly what it is. The lower activation energy matters more than the partial charge.
Okay.
All right, so net result of these, if we're not writing out the entire reaction again, when we come back from break, we'll write out the entire reaction again from scratch, or the entire mechanism for practice. This is the way it's typically written. It has to happen in two steps, our oxymercuration and then our demercuration. But this is frequently the way it's written. We don't write it as two separate steps, we just write it as one arrow with a 1 and a 2. First you do this, and that's gonna make our oxymercuration product, and then we get rid of the mercury. So for this molecule, the net result here, we don't need to draw the intermediate. The net result is we're gonna break a pi bonds, add an OH to one side and a hydrogen to the other side. Which side gets the OH and which side gets the hydrogen?
The left side, you get the OH, since we're substituted. Carbon.
Bingo. So we add an OH here. In a skeletal structure, we'd normally draw the hydrogen, but for the sake of showing the new bonds. So there's our net result, and if we put both of those together, that's a water molecule. That's why it's called a hydration. So even if the mechanism is still feeling pretty abstract, at the very least, and this is one of the reasons why OChem has a reputation of being really hard, is that the mechanisms are hard to wrap your head around, especially at first, right? And so it's tempting to just turn this into a memorization. Like, oh, I recognize that. That means it's Markovnikov hydration, which means I have to do that. There's just too much and too many different possible ways to write things to actually treat OChem as just a straight memorization. But I'll pick on pre-meds a little bit. Pre-meds in particular have an approach of sort of a brute force approach to a lot of classes of just, I'm just gonna make flashcards and memorize shit. And that's especially for a lot of biology where there is a lot of memorization involved. But if you try to do that with OChem, the mechanisms are never gonna make sense, and there's too many things that look too similar. So and then the other side of it is that as far as why OChem has a reputation, does the other people that take OChem that think it's really hard tend to be people that are very math minded, that cruise through Gen Chem just by being good at conversions in math and algebra. And OChem has no math, at least not on the surface of it. And so those people get to OChem and all of a sudden, what do you mean I can't just do conversions in algebra? What do you mean I have to understand the concepts too?
It's like visualization.
Right, and those tend to be the two camps of people that I've seen in my history that struggle the most with OChem. If you can treat OChem as just, we're just gonna focus in on a couple of core concepts and apply them as broadly as possible to this class of reactions. It's more work at first, but you get a deeper understanding, and those, if you can do that, OChem is a little bit less daunting. It's still hard, it still requires a lot of work, but it's not insurmountable. So with that in mind, to give you, that's your little pep talk before we take our break. Let's take a 10-minute break, let's come back at 11. And we'll do that again. And we'll answer the other question too.
I really like the saying that doing a lot of flashcards just makes you really good at doing flashcards.
It's true. Exactly right.
That's why I do look for certain things like vocabulary or languages and stuff like that, but yeah, for like classes like this, it's kind of, yeah. Yeah, gonna mind mapping for note taking, have you heard of that?
Yeah. The trick, the hardest part for me is that it's kind of hard, that works, it's great as a study tool, I don't think it works well as a note taking.
No,
Because you need to know the structure before you can do it,
it's
right?
like take notes traditionally and then later go back and
And
like.
construct, yeah.
Yeah.
Yeah, that's really helpful, and that's one of the main reasons. So why do we still have to take college classes in general? Instead of just, because all the information's online, right? There's no reason that you need to be here to learn this stuff, except that I have the experience to see how all this stuff fits together and present it in the way that makes the most sense. If you just sat down and started learning, I'm gonna learn this reaction, this mechanism, then it really does just become memorizing it, there's too much to memorize. So what a formal education really does get you is that sort of framework that allows you to start constructing your own mind maps. And what a graduate degree in the sciences is supposed to do, and a master's in anything basically is supposed to give you the expertise and the experience to come into a totally new field and do that for yourself.
Yeah.
To start seeing how things fit together and constructing your own mind maps and structure things around how things relate to each other. You don't get that from a bachelor's. You get that from a grad level degree, and then a PhD is you then take that and do science with it. You know, put it together in a way nobody else ever has, or study a subject nobody else ever has because they didn't think about it that way. And that's why there are separate degrees, those sort of levels, and what they kind of represent. It's not just a gateway to getting a better job, although it is that too. But what you're really showing is not, with a bachelor's, is not just that you know all the stuff, it's that you can learn stuff. And master shows not only can you learn stuff, you can learn stuff on your own.
Do you think that this public education system has any place in evolution?
In evolving going forward, or how we got where we are?
Because you're telling me that you were providing framework for students to be able to understand all this stuff, but you know, the people who came up with this stuff were able to understand it without someone pushing it down their throat. So would you say that we are coddling a weaker generation by forcing education down their throat?
I don't think everybody needs a bachelor's. I think everybody can earn a bachelor's. I think everybody should earn a bachelor's.
Well, regardless of the name, like associate's bachelor's, it's essentially the same thing, different time frame. Like
That's where I would disagree. I think an associate's degree has almost become necessary to function in a lot of jobs in our society. And I think it's mainly because there's more stuff to learn. We have more knowledge, and you have to be more knowledgeable about more things to function in our society. Compared to, you know, pre-industrial revolution, where 2 years of schooling, enough to learn how to read, was all you really needed to function in society, because there was less demand on knowledge and understanding how various things work. You still continue to learn after that in your specific field, but you weren't as well-rounded and able to understand other people's jobs. Somebody who worked as a tanner making leather needed to know how that process worked, but they didn't need to know anything about agriculture. And the way that all of our different fields have sort of interplayed as they got more complex and more necessary for things to continue growing and population to get larger and things like that. There's more of a need to understand other fields. And I think as you can track, as technological innovation increased and the number of years the average person spent in school increased. And I think now we're to the point where a K-14 system is almost necessary.
yeah.
So that's what I see as an associate's degree.
Really, socially oriented and optimistic, or I'm thinking about evolution as like, evolution's supposed to be the human innovation being benefited, not technological innovation. So technological innovation increase, that's human innovation lowering to a certain extent, right? So. is
I think we're
evolution
selecting different things.
or evolving, I guess is the
Well, so
question.
that's not how evolution works though, right? Evolution doesn't have direction.
It doesn't have direction, but it does have, adaptation where.
Right.
If you don't use your muscle, then you wouldn't be in a certain.
Right.
Mhm.
Correct. And I think what I would say is it's not necessarily that we're devolving, but current society selects for different things. Current society selects for ability to work well with others, ability to understand the framework of society at some level and have a basic idea of how the technologies work in a way that you didn't need to 5,000 years ago. And the other thing is that we're used to thinking on like 500, yeah, the Industrial Revolution was only like 400 years ago.
Yeah.
That's not really enough time for evolution really to have made any difference. Now, as advent of agriculture itself,
I learned that for adaptation, however you want to look at it, can't happen within one generation. So 100 years ago was when.
yes,
Vehicles, motor vehicles, so I'm sure that some of our physiological.
Yes. So- and forgive me because I'm not a biologist, but I would say that adaptation happens at the shorter time scale. Evolution happens at the longer time scale. So we have definitely adapted
Yeah.
to comforts of technology within the last 400 years. We haven't evolved, we barely evolved as a species since agriculture was invented 10,000 years ago. We still are dealing with the fact that not everybody processes grains well, right? Look at all the gluten sensitivity and stuff like that, and allergies to gluten. Like, if we had actually evolved to handle grain better, that would actually be a huge asset in an agriculture-based society. We haven't even managed to make that evolution happen in 10,000 years. So thinking on the time scale of 400 years, yeah, there's changes happening. And things are a little bit different than they were then, but I wouldn't necessarily. It's too early to say if that's evolution or what that will lead to in the future.
Problem with evolution versus like devolution would be, it's all linear, straight line, so even if it's going down or up, it's.
Forward.
It's still evolution.
Right, exactly. It's a good question though. I understand. Yeah, and it's the trick is to, like you said, it's all forward. So by thinking in terms of de-evolution, you're placing a higher value on the properties that previous generations had, which is not necessarily, there's nothing. And I saw this all the time. I still see this all the time with kids these days arguments, I call them. I hate kids these days arguments because kids these days are different. They're not better or worse. This generation is not necessarily better or worse than previous generations. They have different strengths.
That's just too general. Say that some things are better or worse. Yeah, let's get specific. What's better, what's worse? Those are different, better, good, and bad.
So this generation, I would say, is worse at memorizing things, much better at source evaluation, being able to know what's fake news than previous generations. Because even I'm the tail end of Gen X. I'm right on the line between Gen X and millennials. And when I was taught how to do research, there were no computers around. When we did our first research projects and essays, we had to go to the library. We had to look up books. And if it was in the library, it was true. And you could cite it as true.
So even if it was incredible in the library, you can say that's true.
Right. That's the way that I was taught as a fourth grader how to do research. Fourth graders now, my son's a fifth grader and has had to do his first few projects. There's much higher emphasis placed on how good is your source, not just did you find a source. And I think that carries forward into the college level stuff. College students today are much better at being able to look at something and say, well, you can't cite a BuzzFeed article and be taken seriously. All right, let's come back to chemistry for a little bit. Let's look at this one more time. I didn't, so I'll have you look at this one, and I would encourage you to start from a blank piece of, or just blank half a piece of paper, and try and draw this mechanism yourself. I'm gonna go run over to the instruction office and get more markers, so I have something that'll show up on the recording. I'll be right back, and we'll work through it together.
Really no trash can in this room?
There's
Oh, there's one there.
That was my blind spot. Sorry, go ahead, Z.
What's with this, volleyball? Is that a part of the progress?
Yes, because this is gonna come in as act as the nucleophile. To come in and attack this carbon and break this bond. And so that's where this oxygen comes from in the intermediate. So. First step first. Pi bond. And it's, we always draw the electrons moving, but this is a case where it really is like this whole molecule sort of gloms onto the mercury. You've got this pi bond that looks like that upside down canoe on top and bottom of the molecule. When it gets close enough to the mercury, it basically just sort of stretches out and gloms onto the mercury. And that's what gives us this shape. And don't forget though to show your leaving group leaving. Alright, so it's a little bit weird also in the sense that it's one arrow, but we draw it as sort of two bonds forming. Because it's not really, it's this triangular shape is unstable enough, it's not really like a two full sigma bonds forming here. It just sort of is you almost think of them as like half bonds, we don't draw it that way. But neither of these bonds is super strong because you're in this strained triangular shape. the d orbital and how big mercury is as an ion allow it to happen, but it's not super stable. And then if we have water around, it comes in and attaches to one of those two carbons. If they're both equally substituted, then there's a 50-50 shot. Maybe slightly off of 50-50 depending on sterics, what else is attached. But for the most, but if one of them is more substituted, the water attaches to the more substituted carbon. Because this is the easier bond to break. And then once we have that, we'll actually show the other step here now. So we broke that. There's our mercury. And we've added water molecule here, so we have an oxygen with 3 bonds. And then we have another methyl group. So this is another intermediate that I didn't show previously. Because once you get here, we have another good leaving group attached to the oxygen here. So we just kick off one of these hydrogens.
And that's where that OH group comes from.
And that's where the OH group comes from. The oxygen is from the water. You just have something around acting as a base. Probably actually the acetate coming in to act as a base and pull off that extra hydrogen. And that's going to give us an OH attached instead of a full water molecule attached. So just a quick proton transfer step with whatever base happens to be around. But since we already made an acetate molecule, acetate can be a base. Sometimes you'll see it too. I'm gonna want to put my eraser. If you're not sure what's going to act as the base, but you know that there's a proton transfer, we don't usually just draw it like this, or just kick up an H plus off into nothing. We need something that it can stick to. If you're not sure what that is, sometimes we'll just use B. Not a boron, it's just a placeholder for base.
But usually it's the
Usually, if you had a leaving group, that leaving group could also be a base. And so usually whatever leaving group has left already winds up being, in this case, the
Since
acetate.
the acetate, which the oxygen has that negative in it.
Exactly. It could even be another water molecule. If we're doing this in water, water can act as a base.
Yeah.
And so not all that, that's why I kind of glossed over it the first time. That proton transfer step is not as important. But that does make it really obvious, right? That OH is that water molecule. The oxygen, I should say.
With the very first step where you have the double bond and that's going to mercury, would it be incorrect? Because like I was kind of just trying to do it on my own and I added an electron pair of the mercury and then had that like go back to one of the other carbons, but because they're not, like you were saying,
No.
they're not two single bonds.
That actually is probably more accurate. That's a mercury having all those electrons in its d orbital. You could certainly draw it like that. To account for both of these bonds forming. That's totally accurate. Some textbooks will write it like that and some won't.
Gotcha.
But that's the extra electrons and the extra orbitals around the mercury is what allows this to happen in the first place.
Yeah.
So you're not wrong to write it that way.
Okay, but there's still, it's important even if you do it that way to remember that those are not like full single bonds, they're not like.
There's, anytime we see a 3-sided ring in OChem, we should immediately be thinking that's gonna break.
Okay.
Because just because if it's, even if it's all SP3 stuff, that's all tetrahedral, they wanna be 109 degrees and we're forcing them to be closer to 60 degrees. That's not stable, it's not gonna last long like that.
You left out part of the molecule up here, right?
Yes, I left off that.
Just the acetate, yeah.
We abbreviate acetate as AC in OChem. It's not actinium, that's an acetate. And right there, see it like that there too. All right, so questions on the oxymercuration step? Takes a little bit of getting used to, and it really is 3 steps, because you can't forget to draw that proton transfer to get here.
For our, like, for testing.
For testing
You always use the proton.
Yeah. Yeah.
We can just write it as the base standard.
Yeah. Whatever base happens to be around, you can pick the acetate, you can pick a water molecule, you could just use base as a placeholder. And then this bottom one, we're not gonna get too picky about showing all the steps, because the exact process of the reduction of the mercury all the way to metallic mercury. It's sometimes a lot of this, the inorganic mechanisms that go along with the organic mechanisms wind up either not being fully understood yet, or just not all that relevant. We make metallic mercury because we take this and we reduce it fully. This is what's called a reducing agent, because it's got a bunch of electrons from those hydrides that are not held onto very tight. So anything around that wants electrons is gonna get them. And the easiest way to think about, though, as far as what the effect is to think, okay, well, if I've got sodium borohydride. These electrons are basically just gonna leave and do an SN2. The same carbon that has the mercury attached. Sodium borohydride is a strong reducing agent, but it's not quite strong enough to do an SN2 here. There are reducing agents strong enough who can actually take this alcohol and take it off completely and turn it all the way to propane. Where specifically you want to use sodium borohydride in this case because it hits the sweet spot. It's a strong enough reducing agent that it can kick the mercury off, but it's not so strong that it's going to pass the oxygen off. Alright, but and again, anytime you see something where the most electronegative element is hydrogen, should be thinking reduction, hydride. I'm going to have a hydride acting as a nucleophile in some way. And that's going to keep coming back as we add more functional groups. Sodium borohydride ends up being one of the most important reactants that we use, because it's a way to go from, say, a aldehyde to an alcohol. You can take an aldehyde and have hydride come in and attack that carbonyl carbon and attach and make a new carbon hydrogen bond. And then it converts it to an alcohol. So it winds up coming back a lot. The main thing to remember about it is it's a reducing agent or hydride source are the two ways of thinking about it. Yes. Yeah, and so in terms of organic chemistry, when we talk about something being reduced or oxidized, we're almost always talking about the number of carbon oxygen bonds. When you oxidize a carbon-based molecule, you're adding carbon oxygen bonds. When you reduce it, you're removing carbon oxygen bonds. So technically speaking, this reaction is an oxidation reaction. If you actually count the oxidation or go through and assign oxidation states for the carbons here. And the way we do this is actually a good review. Oxidation states in organic chemistry, we basically look at all the individual carbons. If you think back to Gen Chem, when we did oxidation states, it was basically just make it whatever it has to be to make the charge add up to 0, right? In organic chemistry, we basically look at every individual bond around a carbon. And if the carbon is more electronegative than what's on the other side of that bond, the carbon gets to keep those electrons. And if it's less electronegative than what's on the other side, the other thing keeps the electrons. So this carbon its more carbon's more electronegative than each of the hydrogens, so it's got 6 electrons. Compared to on the periodic table, carbon has 4, right? So this would be a -2 oxidation state. So it's got 2 extra electrons compared to the periodic table. Valence electrons. If we take this, if we add a carbon oxygen bond at the expense of carbon hydrogen bonds, now it only has 4 electrons. So it's a 0. So the oxidation state went from a -2 to a 0. It got oxidized. So adding more carbon bonds to anything that's more electronegative than the carbon, it can be chlorine, it could be nitrogen, most commonly it's oxygen, is going to oxidize it. And that means a reduction reaction just means you're going to be adding, you're either adding carbon-carbon bonds or you're adding carbon-hydrogen bonds, and you're removing carbon-oxygen bonds. And so that's why we call it a reduction, or a reducing agent. If you brought in a hydride, it's going to come in and attach there. Basically just doing, it's not quite an SN2 because it's an sp2 carbon, not an sp3 carbon, but it's similar. And in that case, we added carbon hydrogen bond at the expense of a carbon oxygen bond, so we're going to make that so that it reduced the carbon by adding sodium borohydride. And like I said, we'll spend a lot more time on that when we start talking about more oxygen-based functional groups, because going from, say, an aldehyde to an alcohol winds up being an important step. Or in fact, what our bodies do is take alcohols and oxidize them and turn them into aldehydes, which is a fun fact. So this is methanol, right? Methanol is really bad for you. Ethanol is bad for you too. Drinking alcohol is bad for you too, but it's not as bad for you. But the first thing your body does when you give it either of these is an enzyme called alcohol dehydrogenase comes in and converts it to the aldehyde version. When you do that with ethanol, you get ethanaldehyde, which is actually a naturally occurring molecule in your body. It's not super bad for you. It's an energy source that then feeds into the electron transport chain, stuff like that, which is why alcohol has calories. Methanol, on the other hand, when you dehydrogenate it to get rid of it, you make formaldehyde. And that's actually what gives you that nasty headache after you drink cheap liquor or a red wine the next morning. It's actually your body processes the ethanol first, and then when it's done through processing the ethanol, it moves on to the methanol that's present in trace amounts. And when you do that, you make formaldehyde, which builds up in your brain and causes headaches and that brain fog that you get after drinking too much. It's actually, you're literally pickling your brain with formaldehyde when you drink cheap liquor. And also because that enzyme prefers to break down, it binds more strongly to ethanol than methanol. If you accidentally drink methanol or antifreeze, it's the same enzyme. The treatment for it, if you go to the hospital, is to drink more ethanol. Because basically you can slow down how fast your body makes formaldehyde if you flood your body with ethanol instead. So I had a buddy's dad went camping, and in the middle of the night, he grabbed the wrong water bottle. He had 2 water bottles, one that had methanol for the camp stove and one that was his drinking water bottle. In the middle of the night, he grabbed the methanol one and drank like half of it.
How do you not notice that?
I assume he just chugged it. Like, and you don't always notice the taste right away. And so he had to go to the hospital, and the hospital's like, okay, well, there's a liquor store next door. What's your alcohol preference? And so they got him a boxed wine, because he drank wine, was what he answered. And his job was to chug that wine, and it kept him from going blind. And it's the same thing with antifreeze, because antifreeze is ethane diol. And so it's the same enzyme and the same issue. And so you can slow it down if you flood your body with ethanol, which is not nearly as nasty to your body as those other 2. Oh no, I've got to have a drink.
Never gonna forget the first time I underestimated wine and drank like most of a bottle. In like late high school, and yeah, I'd like to regret that one fairly.
This is also the reason why if you have a really bad hangover, one of the best ways to lessen it is to have a cheap light beer the next morning. Because you'll actually get a fair bit of water out of it because it's cheap light beer, and adding a little bit of ethanol will take the edge off because you'll stop producing formaldehyde for a little bit while the Advil can kick in. There is science showing that a morning after beer is actually helpful for a hangover.
Here I am.
All right, so net result for this oxymercuration demercurization. We added OH, we break the pi bonds. We add an oxygen, an OH group to the more substituted carbon and a hydrogen to the less substituted carbon. All right, in that process, the way we select that, that's called Markovnikov's rule. Markovnikov's rule is when you do an addition reaction, you add the non-hydrogen substance to the more substituted carbon. Substitute, not substance. Right, so if we're just adding HBr, like that first electrophilic addition we looked at. We add the bromine to the more substituted carbon.
But for this one, it would be the water.
In this case, the oxygen goes to the more substituted carbon. So for B here, same general idea. Break pi bonds, add an OH to one side, hydrogen to the other side. So it doesn't, and this is one of the other reasons why memorization doesn't particularly work, because you still have to be able to recognize this is an alkene. This is a Markovnikov hydration, and then no matter what, you gotta be able to look at this molecule and say, this is the active part of the molecule here. And here's what I do. That's hard to put on a flashcard. Doesn't stop people from trying. I'm sure it does. All right. I also like to take OChem as an opportunity to tell any pre-meds that it's a really good idea to go biochem instead of straight biology, because there's a lot of people that hit OChem and decide, I'm never taking more chemistry again in my life. I'm going to go straight bio after this. So being biochem or chem as a pre-med actually sets your application apart a little bit, because you're basically taking the route that shows you can learn how to think about things differently and not just memorize stuff. So we're gonna break here. Doesn't really matter what the rest of the molecule is, you just have to be able to recognize which side is more substituted. We add OH here. We added the hydrogen there.
There's still two more.
Yes. This is just a new bond that was formed. And there's still another one here too. All right, so quick note, and I'm not sure what happened to the slide on this. That first mechanism we looked at with HBr. We had a net result here that was break the pi bond, got a hydrogen to one side and bromine to the other, right? Because we went through that mechanism that looked like this, where we made the intermediate. And then the bromine came back, I should say, to attach there. So this is actually a really clear example of why Markovnikov's rule is the way it is. If you have to make a full-on carbocation intermediate in the process of your reaction, it's going to be on the more substituted carbon. And it also means that you're open to a rearrangement. So if we took that same molecule, so actually before we get there, if we did this reaction, same molecule I just drew, plus plus H2O, and a lot of times we'll write it with an acid catalyst or with sulfuric acid. This is also gonna be a hydration reaction. We're still gonna add an H2O to this molecule to make an OH group on one side and hydrogen on the other. And it's still going to work the same way initially to make a carbocation. You're gonna start with, H2SO4. Your pi bond comes up here and grabs the hydrogen. It's still gonna make the same intermediate here. So this is acid catalyzed hydration. Acid catalyzed hydration is the same mechanism as the hydrobromination addition. It's basically just, you start by breaking the pi bond because it gets protonated. And you make a carbocation. Whatever nucleophile you have around is going to be attracted to that carbocation. Then it's basically just looks like an SN1. It doesn't matter what this nucleophile is, right? For SN1, once you make your carbocation intermediate, whatever has electrons around is going to come in and attach to that carbon. Right, so for acid catalyzed addition reactions, if all they are is acid catalyzed, then you have to be watching out for rearrangement as well. Right, so if I switch this out to that molecule or that from the previous examples. If we protonate this one to make an intermediate. Now we can go through rearrangement. So for the acid catalyzed hydration and acid catalyzed addition reactions, pay attention to rearrangement, just like with SN1 and E1, because we're making a full-on carbocation intermediate. So the full product, if we did the acid catalyzed hydration here, the next step is going to be hydrogen moves over to make the tertiary carbocation. And then water can come in and act as nucleophile here. So we actually wind up putting the OH on the new most substituted carbon because we had that carbocation
The
rearrangement.
sulfuric acid's only for like the hydrogen part, it's not.
Exactly, it's just there to provide, it's hydrogen sulfate, the base, the conjugate base you get when you protonate sulfuric acid is super bad nucleophile.
Oh, okay,
So-
so it'll be like very like sterically,
It's sterically, and it's just fairly stable on its own.
yeah.
And so we frequently in organic chemistry will use sulfuric acid as a catalyst, just as a proton source to kickstart this, because the conjugate base is gonna wind up competing. If we use HCl as the catalyst, now we've got to worry about chloride being involved too, so we actually have two competing addition reactions. If we don't want to deal with that, we just use sulfuric acid.
And just because if there wasn't any sulfuric acid, H2O is so stable, it would just be a really, really, really slow reaction, like it would still
Yeah.
happen.
It would still happen, but you would have to deprotonate this. You can have a base catalyzed
Okay.
reaction, but it's not going to be nearly as fast. So we should use the acid catalyzed, and this is our most common acid. Although sometimes to avoid the confusion with it, sometimes you just see it as H plus as the catalyst, or even just writing the word acid. And almost always when you see that, it's gonna be sulfuric acid. You don't want to use nitric acid, it's also a strong acid, but nitrate's a decent nucleophile and causes other things to happen. Chloride, bromide, iodide, all the other strong acids, they wind up competing, causing other things, so sulfuric acid is the nice sweet spot there. All right, so the other point I was trying to, besides putting this on your radar, that we have just regular acid catalyzed hydration. One of the reasons why, in addition to acid catalyzed hydration, why we have oxymercuration, why do we need separate mechanisms for the same reaction? It's because this one won't rearrange. You don't make a carbocation in that mechanism, right? You make this instead.
Because of the mercury.
Because of the mercury. So they're both Markovnikov hydrations. But just the acid catalyzed one will rearrange if you're not careful. But
This one can't.
This one can't rearrange. So that actually gives us, that's also a useful way we can, if we want it to rearrange, we can use the acid catalyzed one. If we don't, we use oxymercuration. And if it doesn't matter, we use whichever one gives us, like if it's a molecule that won't rearrange, we use whichever one gives us a better yield. If we're doing this in industry, we would just test them both. I believe oxymercuration gives a yield that's closer. This step is irreversible. Actually, this is a pretty irreversible step too, so you wind up with this not being an equilibrium mechanism, whereas the acid catalyzed hydration.
That one's
is.
always an equilibrium.
So this being irreversible means you're gonna get better yields. It's not truly irreversible, it just means that equilibrium favors the products by so much that it won't happen to a significant amount backward. Which is usually what we want in industrial application, right? We don't want our pharmaceuticals spontaneously reacting backward to make our starting material. Although that is one of the main things that can happen why pharmaceuticals have a shelf life. The two main things that cause the breakdown is they either go back to make something more stable in equilibrium, or they oxidize because they're exposed to oxygen. Stuff that's still sealed will last well beyond its expiration date because it hasn't been exposed to oxygen. Once you open it, expose it to oxygen, you start to pop. That gas that's in those pill bottles usually is straight nitrogen to limit oxygen exposure.
During COVID, there were so many inversions with Medicaid, we were having to extend expiration dates by like 6 months, a year in some cases.
Right, and what they would do is they would bring in the chemist. And the chemist would look at it and look at storage conditions like, yeah, you're probably good. It's probably still 90% the right medicine. Basically just like sliding down the acceptable tolerance levels a little bit based on what the medication was and how past the due date it was, that kind of thing. All right. The other wrinkle to this is if this reaction works beyond just hydrations. Because, let me go back to the mechanism. We used water as the nucleophile here, right? To break up this intermediate. Is there any reason why we couldn't use something else as a nucleophile? Oxygen tends to work the best here. Oxygen and nitrogen, we don't see like chlorides or bromides used here as a nucleophile. But basically anything that's got an oxygen, any other alcohol especially, can be used as the nucleophile here. And all that means is instead of just getting a pure, or instead of getting alcohol, we wind up making an ether. So if your nucleophile here isn't water, you still wind up with this oxygen coming in and getting attached to the more substituted carbon. It's just whatever is on the other side of that oxygen isn't just another hydrogen anymore. Now, instead of just being another hydrogen, it's an ethyl group. Because you still wind up with the same intermediate. So here's our mercury down here. Get the rest of the molecule. And then OAC. We still wind up with that same intermediate. If water was the nucleophile, it would come in here and attack there, just like we saw before. We get the net result of break a pi bond, add an OH to one side. In this case, when we break the pi bond, we wind up with the mercury still attached to the more substituted carbon. And then over here, remember, ET is just an ethyl group, right? So if we do this with ethanol instead of water, we get this molecule, which then can do the same proton transfer.
So it just kicks off the.
And we make, instead of making an alcohol attached to the one side of the pi bond, we made an ether attached to the more substituted side of the pi bond. Same mechanism, same steps, same net results, almost. So drawing our final product here. If it's ethanol being added, all the carbons that were already there stay in the same place. That's one of the keys to these, right? Just start by redrawing your carbon skeleton the same way it was. On the more substituted carbon, we added an oxygen with an ethyl on the other side if we wanted to draw it as a skeletal structure. Our final product will look like this, instead of just
And what's the hydrogen on?
and a hydrogen on the other one. And in the interest of just keeping it the same, it would be fine to write it like this so you can see the pieces a little bit better.
So even if you use ethanol, it's still gonna be the same thing as the water, and even if you use the mine down there, it's gonna be just the same thing, but nitrogen instead of oxygen.
Exactly. In this case, we attach a nitrogen where the oxygen's attached. Right, so it's really a whole class of reactions. We don't call these hydrations anymore because we're not adding water, we're adding these other molecules instead. But it's still a Markovnikov. We wouldn't really call, we could call it an oxymercuration at this point, but this would even be an oxymercuration, so we're not adding oxygen. But it's still a Markovnikov addition.
Nitromercury.
It's just gonna be a nitromercuration or something, how we would call it. It's the same mechanism though, so it still gets classified the same way, so I would probably continue to just call it oxymercuration. Because we're still oxidizing that carbon,
No, that is true.
we're just doing it by adding a nitrogen instead of an oxygen.
This really gives you a very high degree of control with the reaction.
Exactly.
Yeah.
All you have to do is switch these out and you get different molecules and you don't need to worry about rearrangement.
And it's almost irreversible. So you're like-
And it's pretty much irreversible, especially once you do the second step. The problem is that mercury is just particularly nasty to deal with and get rid of. You know, if you're working in a chemical lab for your entire life and it's the same reaction you're studying all the time, you probably want to limit your exposure to mercury. This is historically, and even it's one of the best catalysts we have because of the specificity and because of the high yield. But there's also a new field of chemistry called green chemistry, where basically they're trying to go back and find more sustainable, healthier alternatives to using some of these heavy metals. The problem is that, you know, using aluminum acetate doesn't give you nearly the yield that mercury acetate does. Even aluminum's not great for you long term, but it's a lot better than mercury is. So, and it's still taught this way because this is the classic way of doing it. Whether this gets phased out in the actual working labs remains to be seen. Side note, since this is about as far, we already talked about rearrangement, the next slide is just no carbocation intermediate, therefore no rearrangement. This type of mercury this is actually not this one in particular, not mercury 2 acetate, but organic mercury compounds are actually the really dangerous type. Mercury is a metal, it's not good for you, but it's not actually the term is bioavailability. Basically, is how readily does it get absorbed into your body. The bioavailability of metallic mercury is actually really low.
Unless you have like a cut on you or something, then it might.
You'd be surprised. There was actually alchemists in the Middle Ages that used to think that eating mercury was like a cleanse. It was one of the first dietary cleanses.
So it's.
Yeah, I think it was Newton. That's who I'm thinking of. Used to drank pure mercury, but it didn't kill him the first time.
Right.
It was like over 10 years, you got progressively more crazy because mercury bioaccumulates in the brain.
Passes the blood brain barrier.
Once it passes the blood-brain barrier, it tends to stick there. But it's not that bad for you. I had mercury-based toys when I was a kid, and I broke one, and I played with the raw mercury with my hands. It's no big deal. Back in the day, they used to just give kids, in the 60s, they would just give kids a little bit of mercury to play with. Here, check this out. This is
No,
cool.
my mom, she used to play with mercury. Oh, she lived in Mexico for she was born and raised there.
Mhm.
She used to just play with mercury all the time and just like throw it at her friends and.
It's really funny to actually touch something with metallic mercury because it's so much heavier than you think it should be, because it looks like a liquid, right? So you're expecting it to be like the density of water, but it's about 13 times denser.
Watching a video of someone trying to flush mercury down a toilet, it
It just sits there. When you pre-attach the mercury to carbons though, then it actually passes by the lipid, your phospholipid bilayer, it's much easier. So organomercury is really, really dangerous.
because then it stays in your fat.
It stays in your fat or in your brain or wherever, but it absorbs through the skin really quickly. There's, it's just within the last 10 years, because it was since I started teaching, that a researcher at PhD doing a postdoc at some school in New England was studying organic mercury. And when she was preparing an NMR sample, she got a drop of it on her wrist above her glove. And didn't even notice it at the time, and 2 weeks later she was dead. So some of these things are exceptionally dangerous as soon as you start attaching mercury to carbons. So we are going to avoid using mercury. I don't think we do any of the labs where we use mercury as the catalyst for that reason. But in general, those organic metals, they're interesting that way. They behave differently.
And that's where the chemical engineering comes in to like see how you just can do it automated without
People, replace the expensive / dangerous / it's, I mean, we live in a capitalist society, right? So it's the engineering part is all about how do we minimize costs, not really how do we make things safer. But getting rid of mercury waste is really expensive too. So even the pure capitalist engineers still want to get rid of mercury as much as they can, so they don't have to pay to get rid of it. It has the side benefit of them being able to say, look, we didn't use any mercury, none of our workers are dying. But side note about mercury, just while since we have a couple minutes left. Does everybody know the Mad is the Hatter? The Mad Hatter from Alice in Wonderland comes from mercury. The hatters, the people who made hats in early industrial revolution in England, would use mercury on the felt to get it to set and hold its shape. And they would frequently, since they were in a rush and they were going fast, they would frequently use their lips to wet the felt after they put the mercury on it. And so that eventually started accumulating in their brains over time. And after you spent 10 years working in a hat factory, you lost your mind, literally. And so that's actually the Mad Hatter is actually a direct result. That was a thing. The phrase "Mad as a Hatter" exists because hatters literally went mad in the Victorian England days. So-
And the Mad Hatter was working for Wayne Enterprises, making an organic compound that had mercury in it.
There you go. One of the few times that comic books actually did something halfway plausible.
Yeah.
All right, everybody, we're gonna end there. Quiz this weekend. It's gonna be some more practice. It's probably gonna be it's just gonna be a couple of these type of problems. I'll switch up the reactions and the compounds, but it's gonna be acid-based hydrobromination or hydration or one of these oxymercuration reactions. Pay attention to these. There will be at least one of them or one of these is mixed up. All right, everybody, have a good weekend.